when we place a load on a soil mass, it may experience small deformations, and divided by the affected length, those deformations will actually translate into very small strains, such as if placing a small load on a large mat foundation for the basement of a house. On the other hand, when we drive a pile or a slope fails, the deformations are very large and the strain levels are very large. So we have to wonder what controls the different behaviors at small strains and large strains in a granular material. When we are in the lab, we actually reproduce these systems. For example, if we take a specimen and we confine it, and then we apply a deviatoric load, when we plot sigma deviatoric with respect to the shortening divided by the initial length, in other words, the strain in Z, this may look something like that. And at the beginning, we are in the small strain regime. Towards the end of this load deformation, we're in the large strain regime. Now, what about if we take an oedometer and with a very thick rigid wall, so we impose zero lateral strain conditions on the soil mass, and we plot the vertical stress with respect to the vertical strain, then this behavior is actually quite different, because the more we load, the stiffer the material becomes. It cannot deform laterally, and so it will look something like that. At the beginning, we have a small strain regime, and here we are going into a medium strain regime. Now, we could also think of a case where we have a ring shear device where the specimen is held on the periphery, on the annular part of the ring shear device, and in that case, the material will be subjected to very large strain levels in the orders of thousands. Clearly, we see here that there are different strain regimes, and so we're going to start by identifying the small strain, large strain regime, and the very large, the residual condition. In the small strain regime, particles keep their neighbors. They don't lose their neighbors. And so the deformations are limited at the contacts, like when you place your foot on a soccer ball, it's the contact that is deforming. So all the behavior and all the deformations localize at contacts. There is no real friction mobilized between particles, so the energy losses are going to be very small. They're going to be of thermoelastic energy loss origin. The volumetric strains are very small, and therefore, if the loading would be placed under undrained conditions, means that the changes in pore pressure would also be very small. At large strains, particles begin to exchange contacts. And in fact, it doesn't matter if the particle is very rigid or not. It's all about how particles interact with each other and the rotational frustration and friction that gets mobilized. So there are high energy losses. And there will be volumetric strains in most cases, and that could be either dilative or contractive, depending on the initial conditions. That means that if the system was undrained, tendency to volume change would create pore pressure changes. Finally, in the residual regime, when the system has deformed a lot, many things happen. For example, elliptical eccentric particles, they become aligned. If you have mica in sands, the mica platelets were surrounded by grains, and now the mica platelets segregate and they tend to form like a mirror surface, a polished surface on which the coarser particles ride. And if there are coarse and fine grains, they tend to segregate, and the coarse grains will tend to ride on a bed of smaller grains. So in the residual regime, there is particle alignment, particle segregation, and the segregation could be of plated particles or segregation due to size. We wonder what are the regimes that give me the strain levels, that give me these transitions. Clearly, this is not a to be or not to be small strains. These are gradual transitions, but we would like to identify some threshold strains to give us some guidance into the different stages for these transitions. Before we finish with this board, you may wonder, where is the critical state? Well, critical state is a large strain regime where shear occurs at constant volume. The problem is that if I keep shearing the soil and the soil is made of elliptical particles or different particle shapes or particle size, eventually critical state will evolve towards a residual state. So when do we draw the line for what is critical state? Typically, because we run those tests in a triaxial cell and it's limited to 15% deformation, or we could go to 20% deformation, we go to that point and maybe we extrapolate a little bit more to infer critical state, but actually it is a procedural definition. It is a beautiful model to guide our understanding of soils, but recognize that it's not a physically robust limiting state. We will discuss critical state at greater depth in a different video. The other condition that you may wonder is what happens when you actually load in zero lateral strain deformation, like in an oedometer. Well, clearly you do have a small strains, but here, for example, a clay will experience quite a lot of deformation, and in fact there is lots of particle alignment, so somewhere the K0 state or the zero lateral strain condition will fit somewhere here in the middle. Critical state will be somewhere here. And the last case is if you have lots of repetitive loading. Well, that is a weird situation as well, because each cycle may actually be pretty close to small strain, but a million cycles can accumulate significant deformations. That will lead us to another discussion later on in these conversations. Let's try to come up with an estimate of what are the threshold strains that will separate this small from large strain behavior. And we're going to do it in two cases. First of all, we are going to do it for the case of coarse grain soils. And in this case, consider the following situation. We have a particle on top of two other particles, and we apply a normal load. Then that normal load by equilibrium has to be resisted by these two contact forces. So if the force is N, then the initial condition is such that the force N is decomposed into that direction and this direction for the contacts, and this will give us the component coming from the right, and this will give us the component coming from the left. So if this is a triangular configuration, this is going to be 60 degrees, this is 30, and therefore the force here will correspond to N over 2 and N over 2. So R, the force coming from the right, R, times cosine 30 is going to be equal to N over 2. Therefore, R is equal to N over 2 cosine 30. And the L force will be the same. The magnitude of the L force will be the same. If at this point I add a tangential force T, now the configuration of the forces will be different because gradually the particle on the right will begin picking up more and more load while the particle from the left, the contact from the left, is going to be unloaded. And so under this configuration now, the situation is as follows. I have still a force N, and I'm going to have in the limit, I'm going to have only a force coming from the right and the direction of the force T. So by equilibrium, this will be the force T that will bring the contact on the left to 0 force, and then this is the force from the right, and in this case, the force from the right has become equal to the force N over cosine 30, while the force on the left has become 0. Imagine that instead of having that configuration, what I actually had in this triangular system, I had a spring here and another spring. What happens between the top and the bottom is that each spring was resisting a force N over 2 cosine 30, but at the end, this spring stretches out, and this spring confines as this one becomes unloaded, and this one receives a load which is twice higher. That means that from the point of view of the left, this is going to stretch out, and from the point of view of the right, this is going to shrink. If we rotate these points until they meet, then the intersection point, that means that the center of the upper particle has experienced this displacement. And now, in order to go from the particle scale to the macro scale in a very simplistic way, we can divide that displacement, divided the center to center distance, which happens to be the particle diameter times cosine 30. So this is the particle diameter cosine 30. And if we divide delta by that center to center distance, d cosine 30, then this is somehow a measure of the shear strain at the threshold. At the threshold of losing the contact, that means beginning to change the neighbors. When I replace this by the parameters that govern here, you're going to see that this is going to be proportional to the applied force N divided the stiffness of the springs, which, by the way, I can relate to macro scale parameters divided by the diameter square and the length, and I can conclude that this is going to be proportional to the applied initial stress divided the modulus of the particles. Let's say the Young's modulus of the mineral that makes the particles. And this is a wonderful relationship because it gives us an idea of what will control the threshold strain. And it makes sense because the more rigid the particles are, imagine that you're standing on your two legs and the legs are very rigid, it's very easy to push you sideways and for you to lift one leg. But if you were subjected to high initial stress, or the stiffness of your legs was lower, so your knees would be bent, then it would take much more deformation to actually make you lose a contact between your foot and the floor. So this is quite a nice expression. The only thing I should add here is that the actual force deformation of these contacts is non-linear. It's not just a linear spring. It actually looks, because of Hertzian behavior, the normal force of the equivalent spring with respect to the deformation is going to be something like that. So if your initial condition was here, then during unloading of the left, you're going to experience so much deformation, and now during loading of the right, you are going to experience only this amount of deformation compared to this one. And so the unloading is going to be more pronounced, the extension is going to be more pronounced than the contraction. And when you do all this carefully, now this becomes real to an exponent 2/3. The reason is because this is a Hertzian contact. But we still want to highlight the main point. The threshold strain will increase with confinement and decrease with the stiffness of the mineral that makes the grains. Wonderful work done by Vucetich and Dobry and by some of our Japanese colleagues on the threshold strain for sands. Now, what about in fine-grained materials? And in this case, we have a dilemma because we cannot think of solid-to-solid contact. In reality, there is an adsorbed layer around every particle, regardless of the size, but that adsorbed layer is very small compared to the particle size in sands, but becomes very relevant in clays. And so now we cannot think of solid-to-solid contact and a Hertzian contact. Particles actually feel each other before they touch each other, and they interact through electrical forces. And so now we have to think in a different way. So let's say that this is a particle, and it's interacting with these other particles through their double layers and the osmotic pressure, double layer repulsion, van der Waals attraction. And let's say that these particles is of a thickness h, and there is a gap between them, which is gap. And so the question is, and we're going to do it in terms of longitudinal strains, but eventually in the soil mass with particles in all directions, we convert directly to shear strains. So now what would be the threshold longitudinal strain at which the particles stop feeling each other? Well, we could say that this will be a deformation. So it will be a deformation over the initial length, and the initial length between the two particles is actually height plus g plus the gap. And we're going to say that that deformation is going to be some alpha percentage of the double layer thickness, which we may have used this symbol or the beta symbol for double layer thickness in previous presentations, but once again, we're talking about the double layer thickness, the Debye-Huckel length, which is in the order of some nanometers. Now, what about the lower part? Well, let's factor h, and so if we factor h out, this is h 1 plus g over h. And what is g over h? Is the gap divided the height. Now, if I multiply times area, gap times area is the volume of voids, and h times area gives me the volume of solids. So g over h is volume of voids over volume of solids, which is the void ratio. So now I have alpha times the double layer thickness over 1 plus the void ratio. Now, what about h? What macro scale measurement can we do easily that will be directly related to h? Once again, I'm trying to go in a very trivializing manner from particle scale to macro scale parameters. Well, remember that the specific surface of plate-tip particles is going to be equal to two areas, the upper and the lower one, two areas, divided area times height. That's the volume of the particle times raw mineral. That gives me the mass, so area over mass. Now area cancels out, and the specific surface is equal to 2 over h rho m. Therefore, h is equal to the 2 times the specific surface times the raw mineral. So now I can come back here and replace h that was in the denominator by alpha, a percentage of the double layer, and now I will get 2, 1 plus E, and in the numerator, specific surface times raw mineral. This is also a very insightful expression. It tells us that the higher the specific surface, the higher the threshold strain, where I will go from small strain to large strain behavior. Second, it tells us that depends on the double layer thickness. That means that if you are dealing in a material that has a narrow double layer thickness because there is high salt, a marine clay versus a lacustrine clay, the marine clay will have lower threshold strain. It will be more sensitive. Finally, notice that the void ratio is inversely proportional to the confinement. The more you confine the soil, the lower the void ratio. So that threshold strain actually, by the fact that the void ratio is inversely proportional to stress, this will flip over and the threshold strain will be proportional to the confining stress. Summary. If we go back to coarse grain materials and contact behavior between spherical particles, Hertzian type, we saw that the threshold strain increases with the confinement. When we think in terms of fine grain materials, that is still the case. The threshold strain increases with the confinement, but it also increases with the specific surface and with the thickness of the double layer. For example, the threshold strain for Mexico City soils to experience destructuration, the breaking of the structure, can be as high as few percentage, 5%. However, the threshold strain for a near surface sand at 100 kilopascals of confinement is going to be quite small, in the order of 10 to the minus 3. And this is predictable with these simple equations that tell us the governing parameters for the transition between small strain to large strain behavior.